Right, so the subject, electronic engineering circuits and devices, basically, we will be dealing with the analysis of circuits that include semiconductors. That's the electronic part of the course. Right. So the first thing that we will do is an introduction to semiconductors. This is our lecture number 1. So in order for us to understand how semiconductors work, we have to look at the atomic theory of matter. I'm sure you did this in physics and in chemistry. This is basically what you have to do. So atomic theory of matter, it's simple. It says that matter is made of atoms with electrons that are in orbits, and also it has protons and neutrons in the nucleus, right? Though in simplistic terms, we talk about matter as made of very tiny particles and the like and the like. The tiny particles are the protons and neutrons, which are in the nucleus, and the electrons which orbit around the nucleus, right? So in the particles, electrons are the ones which have a negative charge. So whenever I talk about negative charge in electronic engineering, we are talking about the electrons, because those are the ones which have the negative charge. Then protons, they have the positive charge, right? So you realize that when you talk about the positive charge, we are basically referring to the protons, and the neutrons. These are electrically neutral, right? So theoretically, you realize that there are some physics which will break the neutrons into protons and the electrons and the like, and energy. But as for us in our study, we are not too much concerned about the neutrons at the moment. Our main focus is on the protons and the electrons. Electrons making the negative charge, protons making the positive charge, right? So now, we now talk about electric current. Remember, we said current is the movement of charge per unit time. So when a certain amount of charge moves in a certain period of time, then we say there's a flow of current. So electric current is a result of the interaction of charged particles, right? Remember, from now onwards, when we talk about charged particles, we're talking about the electrons and the protons, okay? Those are our charged particles. So when they interact or when they move, then we talk about the flow of electric current, right? So what are the charged particles? In electrolytes, we'll be talking about ions. I don't have to explain much about ions, but you know that they are produced from charging of atoms, right? Either by losing or by gaining electrons. Remember, it is only the electrons which are in motion when we make reference to an atom. The protons and the neutrons are bound together in the nucleus by the nuclear forces. So in the metallic conductors, our charged particles that carry current are the electrons, right? And then in semiconductors, which are going to be our main focus in this course, they will be talking about electrons and holes, right? But then when you check from what we're talking about, there's nothing about a hole, but here we're introducing something called a hole. So I just said it is the electron that moves, and any other particles are bound by the nuclear forces. So what it means is when you talk about a hole, we are talking about a space that is left when an electron moves, right? So let's say we have a positive and a negative. This is just a simplistic view, right? Positive and a negative, right? Then when this electron moves out, right, of its orbit, we now have an excess of positive charges. Remember, an atom on its own is electrically neutral. That means it has the same number of protons as electrons. But then when one electron moves out, what is left is a net positive, which is now a hole. So in other words, a hole is created when an electron moves from its orbit. That's why it creates a hole. In other words, we have a deficit of electrons to create a hole. In insulators, there is no movement of charge, so there is no conduction. So electrons circle the nucleus in shells, right? So you realize that the first shell, which is the K, it can take up to 2 electrons. The arrow can take up to 8. The M can take up to 18. N can take up to 32, right? And within each shell, electrons are further grouped into subshells. There's a shell S, which can take 2 electrons. A shell P takes 6. D takes 10. F takes 14. So our electrons are assigned to these shells and subshells from inside out. Now, from our theory, we know that an atom is electrically stable when it has 8 electrons.
Sorry, excuse me, sir. I'm not sure if it's my side, my network, or what, but the screen is not moving for you.
Is it the same with everyone?
Yes,
it's not moving. Like it's not. We're still on the first page, the introductory page.
Oh, it's not moving. Okay, let me
Yes,
see.
sir.
All right. Let me see what I can do. Let me stop sharing. And start afresh. I think maybe, okay. I checked the, okay. I didn't share the PowerPoint presentation. What about now? What can you see?
yes, it's now
it's
doing
now
so.
clear.
Okay, so
Yeah, it's moving now. Thank you, sir.
I had not shared the PowerPoint presentation. Anyway, let me move fast from when I started. So we said matter is made of atoms and electrons, protons, neutrons. Electrons have negative charge, protons have the positive charge, and neutrons are electrically neutral, right? Then the electric current is a result of interaction of charge or the movement of charge. Ions carry charge in electrolytes. Electrons carry charge in metallic conductors. Electrons and holes carry charge in semiconductors. And I was explaining how a hole is created, right? That's where I was explaining that the hole is created in this way. So I was saying when you're creating a hole, you lose an electron, and what is left is the hole with a net positive charge. This is what I was explaining here, right? Then there's no conduction in insulators. Then I was explaining that the electrons around the nucleus in shells, K, 2 electrons, L, 8 electrons, M, 18 electrons, N, 32 electrons, sharp cells, S, 2 electrons, P, 6 electrons, D, 10 electrons and F 14 electrons, right? And I was saying you assign shells inside out. So what does that mean? Well, it means that from the inside you have the K, then you have the L, you have the M, you have the what? The N. And within the K, that's where you have your S, whatever, P, D, and F. So what does that mean? It means K, if K can contain 2 electrons, it means it's only as an S subshell, right? Then this one which contains 8, it means it has an S and L and a P. The one which contains 18, it is an SP and a D. The one that contains 32 is all the subshells being filled. And I was saying an electron is, an atom is electrically neutral, right? But it is stable when its outer shell is 8 electrons, which is a complete octet, right? That's why we group our elements from group 1 to group what? To group 8, right? 1 having 1 electron in the outer shell, 2 having 2 electrons in the outer shell, up to 8. And our 8 are the stable or innate, the stable atoms. If you don't know much about this, go and check your periodic elements, right? Periodic table of elements, I mean, it will show you what we're talking about, right? So our main semiconductor that we'll be looking at is silicon. Silicon has 14 electrons, right? So it has 2 in the K, 8 in the L, and 4 in the M. But we said an atom is stable when it is 8. So here we have a deficiency of 4 electrons in silicon. So silicon now, for it to achieve a stable octet, it should either gain 4 or lose 4, right? So it either gains or loses 4 electrons. In other words, it means it needs the same energy to either be stable with 8 or be stable with 4. Hence, it is the same conductor. That's why it can act either as a conductor or an insulator. We explained that at a later stage, right? So let's put a comparison between insulators and semiconductors and metals in terms of energy. So electrons can exist at different energy levels, right? So when we're talking about those shells are at different energy levels, but there is what we call a valence band, right? This deals with the number of electrons required to make it stable, right? Then we have what is called the conductance band. This is the band in which if an electron gets to that energy level, it will start being able to move and hence participate in the movement of current. So let's say this is our conduction band, which is definitely a higher band in terms of energy. So for a conductor, we have an overlapping of the conduction bands and the valence band. Like I said, valence band, that's the energy level which is just natural to an atom, the one which contains valence electrons, right? Then we are saying for a conductor, that energy level is a point of intersection with the conduction band. In other words, there are electrons in conductors which do not need energy as long as we are above absolute zero, which do not need energy to start being free to move. That's why we say conductors have a pool of free electrons. They can already move because they are already in the conduction band. Then for a semiconductor, there is a gap between the valence and the conduction band. And this gap is the one in which we should supply energy to electrons there so that they can jump and be in the conduction band so that they can start participating in the movement of charge and hence cause conduction. And we are saying it is possible to supply such energy such that the electron which is here can also gain enough energy to get into the conduction band. Then with insulators, the gap is very large such that no practical amount of energy can be given to the electrons so that they can achieve this energy level. That's why we are saying insulators cannot conduct electricity, because the gap is too large, and no matter how much energy you supply, the electrons will not be able to jump to reach the conduction band, which is at a very higher level. Right. Then we go on to insulators and metals. The separation of the valence band and conduction band determine the electrical properties of the material. Insulators have a very large gap. Electrons cannot jump from valence to conduction band. That is what I was explaining. Then it means there is no current that can flow in the insulators. Conductors, with special reference to metallic conductors, a very small or non-existent energy band. Remember, we showed that the valence band and the conduction band actually overlap, right? Then electrons can easily jump to conduction band due to thermal excitation. In other words, for it can also have more electrons moving there, then current can flow easily. In semiconductors, the energy gap is moderate or slightly small. So you can have some electrons which can jump into the conduction band so that the semiconductor can start conducting. When the electron jumps now from that band into the conduction band, right? So we have our electrons there, electrons and our positive charge there in the nucleus. When the electron jumps into the conduction band, right? That's how it leaves a hole. That's how I was explaining how you end up having a hole at that level, right? Then only little current can flow. So semiconductors have limited conduction compared to metallic conductors. So sometimes thermal energy is enough to cause an electron to jump from the valence band to the conduction band. It means by increasing the temperature of the semiconductor, you can actually make it be able to conduct, and this produces an electron hole pair. Why do we talk about a pair? It's because there cannot exist a hole without there being an electron that is moved, right? That's the electron hole pair, right? So electrons fall back out of the conduction band into the valence band, combining with a hole. So if this kind of movement, when an electron jumps to the conduction band, then when it jumps to the conduction band, it leaves a hole behind, right? So it jumps to that, a hole is left behind, so we have an electron and a hole. That's our electron hole pairs. When it falls back by losing energy into that, it recombines and then the hole is destroyed, right? So how can we improve the conduction? We improve that by doping. So to make semiconductors better conductors, we can add impurities or what are called dopants to contribute extra electrons or extra holes to the semiconductor. So we are trying to improve or increase the number of charge carriers. So elements with 5 outer electrons contribute an extra electron to the lattice. Those are called donor dopants. So when we are talking about donor dopants, we are talking about those with 5 outer electrons. That means they are group what? They are group 5 elements. Okay? Those are the donor. Then those with 3 outer electrons, they will accept an electron, right, from the silicon, and they are called acceptor electrons, and those are group 3 elements. So we will refer to this as we explain how we create our types of semiconductors, but we are saying if you add a group 5 element, you are donating more electrons. If you are adding a group 3, it will accept an electron, right? So group 5 are the donors, the donor atoms. Group 3 are the acceptor atoms, right? So we use phosphorus and arsenic as our donor dopants. So those are our group 5. So if phosphorus is introduced into a silicon lattice, there's an extra electron to move around. Remember, we said silicon will require 4 electrons to be stable, but then phosphorus is what? Is 5. So at the end of the day, after producing the stable octet, we still have 1 loosely bound electron that will be able to jump the conduction band and hence improve the conduction, and that is called producing what we call an N-type silicon semiconductor material. N-type because it is an excess of electrons, and an excess of electrons is an excess of negative charge. So sometimes we use the plus symbol to indicate heavier doping in the N. So N plus silicon means it is a heavily doped silicon, right? It's not the charge on the silicon as such. So phosphorus becomes positive ion after giving up its electron. So that is what we are having. If our phosphorus is blue and our silicon is grayish, then we are saying phosphorus, these two combined there, this now stable, this stable, this stable, this stable. So there will be an extra electron there, which will be the red one, which will be easy to move through the lattice and hence conduct. So that's how we create an extra electron. So this electron now is free to move into conduction because it is not bound to anything, because already we have a stable octet in the surrounding elements. Then we have boron, group 3. It contributes a hole if it displaces silicon atom. So boron is an acceptor. It gives a p-type semiconductor, and the boron becomes a negative ion. So in other words, in this case now, boron is 3. So the 3 from boron will bond to 1, 2, 3 silicon atoms, right? But then it leaves a deficit of an electron because it should actually contribute 4, but it has contributed what? 3. So as a result, we have a deficit of an electron, and that deficit is the hole, right? That's how we create that. And because there is a hole, then it's p-type, right? So because of the limit of our time, end here, then restart our video again. So let me stop the recording, then I'll restart maybe at 9:05 for the next thing.